My dear friends, welcome to SEKAR classes on applied data science with Python. This is lecture number 241. In this lecture, I will continue my discussion on SNE. In this particular lecture, we will try to understand a problem known as crowding problem in the context of SNE. This particular problem we will try to understand with this particular diagram. What is this diagram says? We will try to understand. Before understanding this diagram, let me recall one important point what we were discussing in my previous lectures. This SNE, what is the functionality of this SNE? SNE try to preserve. It will preserve. Try to preserve the distances. Try to preserve the distances in a neighborhood. In a neighborhood. In a neighborhood. This could create problems. Let me give you a very simple example. Let's assume I have two-dimensional data. Let's assume I want to project this two-dimensional data into one-dimensional using SNE. Suppose my 4 points, say this is my x1, this is my x2, this is my x3, this is my x4. Let me assume these are the 4 points. Let me assume they are corners of a square in 2D. This length is same as this length. This length is same as this length. Let me assume that this length is d, this length is d, this length is d, this length is also d. As I told you, these points are corners of the square. If I have 4 points like this in 2D space which are at equidistant, so all these points are equidistant. All these points in the sense x1, x2, x3 are all in equidistance. I can say they are corners of the square. These are what? These are vertices of a square. We want to embed them into 1D space. We want to embed all these points into 1D space by using our SNE. That's the basic idea, isn't it? Let's assume that we are defining my let's assume I am defining my neighbors using distance d. I am defining neighbors. Neighbors. What's the criteria for defining neighbors? By using distance d. If 2 points are at distance d, I can say they are neighbors. Otherwise, they are not neighbors. That's the idea. I want to embed my x1. First, let me consider this particular point. Which point? Let me say I'm considering x1. I want to embed my x1. Where can I embed my x1? Let me embed my x1 into 1D space. Let me say this is my x1. Isn't it? Yes. Let me take x2. Where should I keep? Let me take x2. This is x2. What is the distance between x1 and x2? The distance d. Same distance I must preserve in 1D also. Therefore, let me assume I am keeping x2 here. What is this distance? This distance is d. This particular distance is d. Isn't it? This distance is d. Yes. I will place my x2 such that distance between x1 and x2 is d. Just see, That's what SNE says. Same distance must be preserved in lower dimensional space also. In 2D, distance between x1 and x2 is d. In similar manner, same distance I am keeping in 1D also. I will make sure this distance is d. Means distance between x1 and x2 is d. In 1D also, I have embedded my x1 and my x2. Let's take x3. Where is my x3? Yes. Let's take x3. The good thing is x3 is of distance d from x2. Just see x3. What is the distance between x3 and x2 in 2D? In 2D, distance between x3 and x2 is d. Therefore, I can write, let me write this x3 here, somewhere here. Again, same distance d. Here also you have same distance d. Distance between x3 and x2. Distance between, these are the points. These are the points, isn't it? Distance between x3 and x2 is also d. So, I can embed my x3 here, isn't it? Therefore, here also in between x2 and x3, I have distance d. In 2D also, I have distance d. No issue. x1 and x3 are not. What about for x3? x3, what are the neighbor? Only x2. But x1 and x3 are not in neighborhood. What are the neighborhood of x1? My neighborhood of x1 is x2 comma x4. x2 comma x4. x1 neighborhood is x2. What is the reason? Distance between x1 and x2 is d. Why x4 is in the neighborhood of x1? Distance between x1 and x4 is d. That's what it says, isn't it? Not x3. x3 is not x3 because the distance is more than neighborhood. This is x3. x3 and x1, they are not neighbors. These are not neighbors. You cannot say these are not neighbors. x1 and x3 are not neighbors. What's the reason? What's the reason? We are considering neighbors with d distance. What is this distance? According to Pythagoras theorem, if I say this is x square equal to diagonal square equal d square plus d square. Isn't it? Isn't it? It's 90 degrees. Therefore, x equal to what will you get? You will get root d. Therefore, x1, this distance is root d. What is the criteria for forming neighborhoods? D distance. But x1 and x3 are not at distance d. Therefore, they are not neighbors. In the case of two-dimensional space, distance between x1 and x3 is root 2d, whereas in the case of 1d, distance between x1 and x3 is 2d. This is d and this is d, 2d. I need not preserve this distance. Why? Because I don't care. Why? Because in 2D itself they are not neighbors. I need not preserve that distance in 1D, isn't it? Therefore, I can say, let's assume I am defining my neighborhood using distance d. I need to preserve these four distances. This distance I have to preserve, this distance I have to preserve, this distance, these four distances only I have to preserve. I don't want to preserve the distance between x1 and x3. I need not preserve distance between x1 and x3, isn't it? Because the distance between x1 and x3 is root 2d in root 2d, isn't it? Root 2d in two-dimensional space, whereas distance between x1 and x3 is 2d in one-dimensional space. This is my one-dimensional space, this is my two-dimensional space, isn't it? But in the 2D, it is root 2d. In the case of 2D, distance between x1 and x3 is root 2d. In the case of 1D, distance between x1 and x3 is 2d. I need not preserve the distances. Why? Because they are not neighbors in 2D itself, but in 2D it's root 2d. But since x3 is not in the neighborhood of x1, isn't it, at distance d, I don't have to preserve it. Placing x3 is here, okay, isn't it? Why? Because as I need not preserve distance between x1 and x3 as they are not neighbors to each other. Placing x3 is here, okay. Now comes a tricky part. Where will I place my x4? I need to place my x4. Let's take multiple options here. Let's say I place my x4 here. Let me assume I am keeping x4 here. Just say this is my x4. What happens? Distance of d from x1, if I keep this one, what is this distance? Let me say this distance is d. This distance is d, isn't it? Distance between x1 and x4 is d. Just see, x1 and x4 distance is d. Means same distance we are preserving, isn't it? This distance we are preserving. I am preserving this distance. Why? Because distance between x1 and x4 is d, isn't it? My x1 and x4 distance, what I am preserving. But as soon as I place x4 here, my distance from x3 to x4 has become 3d. Just see, distance between x3 and x4, this is 3d. Why? Because this is d plus d plus d, 3d, isn't it? While it should be d. Why? Because your x3 and x4, just see, this is my x3, this is my x4, they are at distance d in 2d, they are in two-dimensional space, they are at distance d. But if I project them into one-dimensional space, distance between x3 and x4 is 3d, isn't it? 3d, while it should be d, right? Because my x4 and x3 are neighborhoods in 2d. Why? Because in the neighborhood of x3, you have x4 and x2. But where will I place my x4? If I place it here, let me say I am placing my x4 here. Let me say I am placing my x4 somewhere here. In that case, what happens? If my x1 and x4, what is the distance between your, if I place x4 here, what are the neighborhoods of x4? Distance between x4 and x3 is d, and x4 and x1 is d. What? This is my x4. This is my x4. What is the distance between x4 and x1? This is d. This is d. This is d. This is become 3d. Why? Because if I keep x4 here, in 2d, distance between x4 and x1 is d. But in 1d, it is become 3d. Distance between x4 and x3 is d. Yes, this distance we are preserving. We are preserving this distance in 1D, but we are not able to preserve this distance. Why? Because distance between x4 and x1 is d. Here x4 and x1 is 3d, isn't it? Wherever I place, just observe this one carefully. The distance will be preserved. We are able to preserve only one distance, either between x4 and x3 or in between x4 and x1. So whatever I do, if I have to place my x1, x2, x3 and x4 points into one-dimensional space, in 1D space is nothing but a line. Whatever I do, I will make at least one mistake. I will make at least one mistake. Isn't it? I will make at least one mistake. Wherever I place my x4, whether I place my x4 here, whether I place my x4 here, whether I place the x4 here, or whether I place my x4 here, whether I place my x4 here, at least place neither of them work. If I place x4 here or here, neither of them work, isn't it? At least one distance will get corrupted. That's important. At least one distance will get. That's what this initial diagram says. Just see what's happening here. At least one distance. At least, let me choose some other color. Yes, at least one distance. At least one distance. At least one distance will get corrupted. Will get corrupted. That's the basic idea, isn't it? So there will be cases like this. This is proof by contradiction. So I'm taking this case where I have my data points like in 2D, isn't it? Like this x1, x2, x3, x4. I am saying I will not be able to project these data points from 2D to 1D by preserving all the distances in a neighborhood. Sometimes, let me say like this, sometimes, especially in the case of hypercubes, it is impossible to preserve distances, in all the neighborhoods, Such a problem is called crowding problem. What it means is your points are getting crowded. It's impossible do whatever. So this is one of the reasons. So earlier before Disney, few years before Disney, there was a lot of research on stochastic neighborhood embedding. Then people said whenever they did stochastic neighborhood embedding, they started observing this problem of crowding. And then they said, let's use T distribution. Stochastic neighborhood embedding. Again, this T distribution is one of the distribution in statistics. It's also called student's T distribution. It's called the student's T distribution, and it has a shape which is slightly different from Gaussian distribution. I already discussed about T distributions in my previous lectures. Even we defined the relation between Gaussian distribution and T distribution. I request you to go through once the T distribution and Gaussian distribution lectures. Why T distribution is used slightly beyond this. Why T distribution is used to resolve this crowding problem is beyond the scope of this class, but T distribution was primarily used. But you must understand, T distribution was primarily used to resolve the crowding problem. Here they are using T distribution to resolve the crowding problem, and by result what it is literally doing is it says, I will not guarantee that I will preserve all the distances. I will do my best. T distribution cannot guarantee that distances will be preserved. T distribution will do its best. What it says, T distribution says, I will do my best to preserve the distances. T distribution is not going to give guarantee to preserve the distances. It is not going to promise. It is not going to promise you that it will always solve the problem. In case like this, it will try to find best trade-off. It will try to find best trade-off. This will try to find best trade-off. Which one will try to find best trade-off? T distribution will try to find best trade-off. T distribution will try to minimize. Yes, T distribution will try to minimize errors. This is the basic idea behind this crowding problems in Disney. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.